If you click this video away, then please tell me what the reason was so that I can improve. Otherwise, hi and welcome. I am trying to learn particle physics. Today, the Large Hadron Collider, and after we've done that, we're going to do standing yoga. And if you participate in the standing yoga, then it's better at your own risk. LHC Extreme Machine. At 27 kilometers long, the Large Hadron Collider, LHC, is the largest machine in the world. Its most distinctive feature, though, is its temperature. At 1.9 Kelvin, a smidgen above absolute zero, the LHC is the coldest ring in the universe, unless an alien civilization has built one that is colder. I never heard that the thing runs at almost absolute zero, at minus 279 degrees something. Okay, let's see. So the thing is 27 kilometers long, and it runs at what? I'm not completely sure if Kelvin is not something like that, but we're saying a smidgen. I don't know what smidgen. It's running at minus 279 degrees Celsius, pretty much, and it is almost not possible to make it colder. Because when the atoms stand still, and I don't know, and when time would stop or something, I don't know what would happen, but it's not possible to make it colder than that. But because when the atoms stand still and you can't make it, yes, but it makes sense, you can't make the atoms in the universe more than standing still. So that is zero. Let's something else. If they get warmer, they are moving faster. We know it. They are also expanding, but that's something else. If atoms get warmer, they are moving faster. It's absolute zero by minus 279 degrees Celsius. They are standing still. My assumption is that you can't make it colder because they are already standing still. If it gets no warmer, they're starting to move faster and faster, these atoms. Does now fast-moving things make something warm? That makes a lot of sense. We're having heliology in another series, and where we're wondering why a protostar gets warmer during the gravitational collapse. Were it not for this searing cold, the LHC might have suffered the same fate as the superconducting supercollider, which was on its way to become the most powerful accelerator in the world before the US government canned it in 1993. The SSC's partially completed 87-kilometer tunnel near Waxahachie, Texas, now lies derelict. What does derelict mean? Killed by a ballooning budget and deficit of innovation. Why was the coldness of that thing important? Whatever. Some people in the United States and Texas in 1993 were also building a Large Hadron Collider, the superconducting supercollider, but there were problems with budget and something else. I can't find the line. With a budget and also a deficit of innovation. Whatever, there were other people who also tried to build such a colliding thing, like the Large Hadron Collider. Keen to avoid a similar debacle, CERN, the European Particle Physics Lab near Geneva, Switzerland, took the momentous decision to cram the LHC into an existing circular tunnel 100 meters underground. This had been built in the 80s for the Large Electron-Positron Collider. It was a decision that led to a carefully choreographed dance of extreme engineering. Okay, people in the United States tried to build such a collider also very long. The biggest machine in the world, and also the coldest place in the universe, the coldest ring in the universe. And Now, when we built it in Switzerland, they used already a pre-existing one which was built as a large electron-positron collider a few years earlier. It was a decision that led to a careful, underground rivers were frozen in mid-flow, components shipped around the world, and superconductors pushed to the limits to deliver the magnetic power that would be needed to curve protons traveling at almost the speed of light around such a tight circular path. I don't understand the part of the underground rivers frozen. Do we mean to build this thing when you can just lead the river somewhere else? You don't have to freeze. It doesn't even make sense. Whatever. They had to put a lot of difficult things together. They had to ship in things, superconductors or other things, so they were able with magnetic power to push these electrons always on. We're going to read that if we have time in a moment. Again, the light is, so the protons or whatever, the particles are pushed along at almost light speed in that ring octagon space? Side. The cooling for the magnets requires liquid helium at a temperature at which it is superfluid with zero viscosity that can slip through microscopic cracks. Okay, these magnets, they are pulling at the particle and kind of, I don't know what we're doing. Maybe they are switching to a side, whatever. And then we're taking the particle and pushing it on and making it a bit faster. And every round it gets a bit faster. Every time taking it and giving it a little force pulling at it and pulling it to the other side. And these magnets have to be cooled for some reason. And they're using helium for it, which is liquid. And that has to be at a very low level, the temperature for the helium, so that it does not have viscosity. So it cannot slip through cracks. Viscosity is how much fluid, how easy it flows. So it has to have zero viscosity. But we're having liquid helium. That means we're having it liquid, but without any flowing power. Whatever. The first attempt to switch on the LHC in September 2008 failed after 9 days. Then a joint connecting a pair of superconducting wires overheated, causing an explosion release of helium used as a coolant, delaying the project for over a year. Let's try to understand that part. No, I don't know what a superconducting thing is. I think it's just conducting. Like some elements to conduct. Iron is conducting quite good, paper not. And there's some elements which really good conduct. Now, and there was, with a joint, two superconductors connected. They overheated, and it caused an explosion that released helium, which was used as the coolant, which probably means to cool. And now we had to wait a year. Now we can do either standing yoga or read the thing again. The Large Hadron Collider at CERN near Geneva, Switzerland is housed in a 27-kilometer-long tunnel. It is commonly described as a ring, but is actually more like an octagon with rounded corners. In the straight sections, intense electromagnetic fields kick to counter circulating beams of protons every time they come past, increasing their speed. By the time of collision, they have reached 99.99% of the speed of light. Bending such a fast-moving beam of particles requires very powerful magnets. Any power lost to electrical resistance would be a brake on performance, and so the magnets are made of supercooled, superconducting materials. Even then, they can only achieve gentle curving, hence the energy's vast size. On 4 of the octagon sides, more magnets constrain the proton beams to a fraction of the thickness of a human hair and bring them into a head-on collision. 4 large detectors record the result, one at each point. Each detector is made up of concentric cylinders. Those closest to the collision point are made of a semiconductor. If an electrically charged particle passes through a semiconductor, it liberates the material's loosely bound atomic electrons, creating a pattern of electrical currents that allows a precise measurement of a particle's path. Magnets surrounding the detector cause the path of the charged particles to curve with a degree of curvature representing the particle's momentum. The next cylinder outwards consists of detectors filled with liquid argon or lead tungsten crystals. Collisions with the densely packed atoms in these detectors stop the mouse particles in the track, and photons emitted as the particles decelerate can be used to measure the particles' energy and so identify them. The heavier variants of electrons, known as muons, aren't stopped by these detectors but are identified and measured by the next cylinder of dedicated detectors. The even more reclusive neutrinos aren't measured at all. Their presence is instead deduced by totting up the momentum of all the other particles produced in a collision and seeing if anything is left unaccounted for. The Higgs boson is short-lived, decaying almost instantaneously into other particles. To infer its presence, we must measure these decay products and look for evidence that they come from Higgs. Fortunately, the Standard Model predicts everything we need to know about the Higgs boson apart from its precise mass. For every possible mass, we can predict the number of Higgs particles that the LHC should produce and what they will decay into. For example, the Higgs should sometimes decay into pairs of high-energy photons. Because momentum is conserved in particle decays, the momentum of the photons can be translated into the mass of the particle that produced them. There are many possible sources of a photon pair, but if we concentrate on the likely-looking ones and plot their combined momentum on a histogram, an unknown particle will make itself known as a bump, an excess of events corresponding to a particular mass. This is what both ATLAS and CMS saw at a mass of around 125 gigaelectronvolts, which was announced to the world on the 4th of July 2012 as the Higgs boson. It wasn't the only evidence. The Higgs boson is also expected to decay into two Z bosons, which each decay further to two leptons. Combining the momentum of these leptons produced a peak at the same mass visible in the photon data. W bosons added their own strand of evidence. These particles decay into neutrinos, which aren't detected, so there is no definite mass bump in this case. Instead, we just see more W decay than we would expect if the Higgs didn't exist. All in all, the evidence was just enough to grab a gold standard 5 sigma discovery, signifying a probability of just around 1 in 3.5 million, but the finding came about as a result of random statistical errors. In other words, the Higgs boson exists. It was a particle physics part. If you were here for particle physics, you can go directly to the next part of particle physics, where we're going to continue with is the Higgs too dull? We're going to do that part about the Large Hadron Collider in mechanical engineering. So, if you were here for particle physics, you can go to the next part of particle physics or to mechanical engineering. If you stay here and participate in the standing yoga, then it's certainly on risk. We just have 2 minutes. Breathe in with the arms up, the feet are standing together. Out, arms down. In and up. Out and down. In and up. Out on the side. In and up. Out on to the other side. In and up, inch space between the feet, out again to the side. Up, come up onto the toes. Out, sink down. Up again. Out onto the other side. Up onto the toes. Out and down. Again, up, reach high. And out, come down, feet again together. Breathe in with the right leg. And out and stretch the left one. Breathe and change. And out, stretch the right one. In into the middle. Out and down. Breathe in with the right hand up. Breathe out with the left leg. Look up to the right hand. In and down. Out and down. In with the left hand up. Breathe out with the right leg. And look up to the head. In and down. Out and down. Breathe in, straighten the back halfway up. Out and down. In, halfway up, straight back. Out and down. And in, come slowly with the round back up. And make it the top of the back with the shoulder. Breathe in, lift the arms up. And breathe out, lean back, draw the shoulder blades together. In and up. And out and back. In and up, intertwine the fingers and reach high. Out, reach in front of the back. In and up, intertwine the other way around. Out and down. In and up. Out, lean back, drop the shoulder blades together. In and up. Lean with long arms back. In and up. Out with the arms down. Breathe in with the arms up. Out and down. In and up. Out and down. And the last time in and up. Bring the hands to touch, lower the hands down to heart center. It was a 2-minute yoga. Thank you very much, and until next time.